Hi, everybody. Let's see again, and let's start our lecture. Okay, so 1 second, please. So, and today, let's continue to study sensor system in engineering. For complex processes with a large number of variables like chemical plant, a nuclear power plant, and many other systems with components located at large distances apart, and systems that have various and stringent operating requirements, like the space station, for example. Centralized direct digital control is quite difficult to implement. In distributed control, the control functions are distributed, both geographically and functionally. Some form of distributed control is appropriate in large systems, such as manufacturing, work cells, factories, intelligent transportation systems, and multi-component process plants. A distributed control system, or DCS, will have many users who would need to use their resources simultaneously, and perhaps would wish to communicate with each other as well. Also, the plant will need access to shared and public resources and means to remote monitoring and supervising. And furthermore, different types of devices from a variety of suppliers with different specifications, data types, and levels may have to be interconnected. A communication network with switching nodes and multiple routes is needed for this purpose. This is essentially a network control system, NCS. In order to achieve connectivity between different types of devices having different origins, it is desirable to use a standardized bus that is supported by all major suppliers of the needed device. The foundation field bus or industrial Ethernet may be adopted for this purpose. Field bus is a standardized bus for a plant, which may consist of an interconnected system of devices. It provides connectivity between different types of devices having different origins. Also, it provides access to shared and public resources. And furthermore, it can provide means of remote monitoring and supervision. A suitable architecture for networking and industrial plant is shown in this figure. The industrial plant in this case consists of many process devices, one or more PLCs, and DSCs or supervisory controllers. The process devices will have direct input-output with their own components, while processing connectivity through the plant network. Similarly, a PLC may have direct connectivity with a group of devices as well as network connectivity with other devices. The DSC will supervise, manage, coordinate, and control the overall plant. A popular distributed control architecture is provided by hierarchical control. Here, control functions are distributed functionally in different hierarchical levels or layers. The distribution of control may be done both geographically and functionally. In hierarchical structure, can facilitate efficient control and communication in a complex control system. Consider three-level hierarchy: management decisions, supervisory control, and coordination between plants in the overall facility may be provided by the supervisory control computer, which is at the highest level, or level 3 of the hierarchy. The next lower level, intermediate levels, generate control settings or reference inputs for each control region or subsystem in the corresponding plant. Set points and reference signals are inputs to the direct digital controllers, DDC, which control each control region. The computers in the hierarchical system communicate using executable communication network. Information transfer in both directions, up or down, should be possible for best performance and flexibility. In master-slave distributed control, only downloading of information is available. As an illustration, a three-level hierarchy of an intelligent mechatronic system, IMS, is shown in this figure. The bottom level consists of electromechanical components with component-level sensing, and furthermore, actuation and direct feedback control are carried out at this level. The immediate level uses intelligent preprocessor for abstraction of the information generated by the component-level sensor. The sensors and their intelligent preprocessors together perform tasks of intelligent sensing. State of performance of the system components may be evaluated by this means, and component tuning and component group control may be carried out as a result. The top level of the hierarchy performs task-level activity, including scheduling, monitoring of the system performance, and overall supervisory control. Resources such as materials and expertise may be provided at this level, and human-machine interface would be available. Knowledge-based decision-making is carried out at both intermediate and top levels. The resolution of this information that is involved will generally decrease as the hierarchical level increases, while the level of intelligence that would be needed in decision-making will increase. Within the overall system, the communication protocol provides a standard interface between various components, such as sensors, actuators, signal conditioners, and controllers, and also with the system environment. The protocol will not only allow highly flexible implementation, but will also enable the system to use distributed intelligence to perform preprocessing and information understanding. The communication protocol should be based on an application-level standard. In essence, it should outline what components can communicate with each other and with the environment, without defining the physical data link and network level. The communication protocol should allow for different component types and different data abstractions to be interchanged within the same framework. It should be also allow for information from geographically removed locations to be communicated to the control and communication system of the IMS. I am now having to present 5 examples of engineering systems that benefit from proper sensor systems, and related instrumentation. A machine that we developed for the head removal of salmon is shown in this figure. The conveyor, driven by an AC induction motor, indexes the fish in an intermittent manner. Image of each fish obtained using a charge-coupled device's CCD camera is processed to determine the geometric features. which in turn establishes the proper cutting location. A two-axis hydraulic drive then positions the current accordingly, and the cutting blade is operated using a pneumatic actuator. Position sensing of the hydraulic manipulator is carried out using linear magnetostrictive displacement transducers, which have a resolution of O dot over 25 millimeters when used with 12-bead ADC. A set of 6-gauge pressure transducers is installed to measure the fluid pressure in the head and rod sides of each hydraulic cylinder, and also in the supply line. A high-level imaging system determines the cutting quality according to which adjustments are made on line to operating conditions of the machine and the parameters of the control system to improve the process performance. The control system has a hierarchical structure with conventional direct control at the component level or load level, and an intelligent monitoring and supervisory control system at an upper level. The primary vision module of the machine is responsible for fast and accurate detection of the geoposition of a piece on the basis of an image of the piece that is captured by the primary CCD camera. This module is located in the machine core and comprises a CCD camera for image acquisition, an ultrasonic sensor for thickness measurement of piece, a trigger switch to detecting a piece on the conveyor, an image processing board for frame grabbing, an image analysis, and an input-output card for data acquisition and digital data communication with the control computer of the electrohydraulic manipulator. This vision module is capable of reliably detecting and computing the cutting location of a piece in approximately 300 or 400 microseconds. The secondary vision module is responsible for acquisition and processing of visual information pertaining to the quality of processed piece that goes through the cutter assembly. This module functions as an intelligent sensor, is providing high-level information feedback into the control computer. The hardware associated with this module are a CCD camera at the exit end for capturing images of processed piece and an image processing board for visual data analysis. The CCD camera acquires images of processed piece under the direct control of the host computer, which determines the proper instant to trigger the camera by timing the duration of the cutting operation. The image is then transferred to the image buffer in the image processing board for faster processing. In this situation, however, image processing is accomplished to extract high-level information, such as the quality of processed piece. With the objective of monitoring and controlling industrial processes from remote locations, we have developed a universal network architecture for both hardware and software. The developed infrastructure is designed to perform optimally with each Ethernet backbone, where each network device needs only a low-cost network interface card. This figure shows a simplified hardware architecture, which networks two machines, a piece processing machine and an industrial robot. Each machine is directly connected to its individual control server, which handles network communication between the process and the web server, data acquisition, sending of control signals to the process, and the execution of low-level control logs. The control server of the piece processing machine contains one or more data acquisition boards, which have ADC, DAC digital input, output, and frame grabbers for image processing, video cameras, and microphones are placed on strategic locations to capture live audio and video signals, allowing the remote user to view and listen to a process facility and to communicate with local personnel. The camera has built-in pan, tilt, and 21 times 21 zoom capability, which can be controlled through a standard communication protocol from the host computer. Multiple cameras can be connected in a daisy chain manner to the video streamer server for capturing and encoding the audio-video feed from the camera. A PCI board is installed in the video streaming server. It can capture video signals at a standard frame resolution of 640 times 480 pixels at 30 frames per second, FPS, with a hardware compression that significantly reduces computational overhead of the video streaming server. In the present implementation, each of the audio video capture board can support only one AV input. AV means here audio video, and hence multiple boards have to be installed. Captures full electrocardiogram and form a data file. Built-in software to process and interpret the signal to assist the diagnosis of some types of heart problems by doctor. Channel selection feature to output different types of process information. Imaging, blood pressure, temperature, and blood oxygen sensing. Medical CCD camera with built-in illumination source. Digital blood pressure monitor provides blood pressure and pulse rate. Cuff is inflated by pressing a button. Digital ear thermometer, pulse oximeter for head and chest models are available as well. But we should note it here. Blood pressure and temperature readings may be wirelessly transmitted to patients and computed by embedded low-power miniature transceiving into the sensor. Sensor power supply capabilities. The following off-the-shelf sensors have the built-in AC adapters near with 50 up to 60 Hz. ACG unit, medical CCD camera, blood pressure monitor, stethoscope, thermometer, and pulse oximeter are typically powered by disposable batteries. Other types of sensors, particularly wearable ambulatory sensors, may be integrated as well. The accessories required for the jacket include complete low-power integrated analog from N to HCG application, one-piece cable with lead wire, Yoke-made 3-lead universal adapter, dry electrode, AMC, and reusable DIN connector lead wire, 3-lead snap connection, step-down converter with bypass mode for ultra-low power wireless application, needle-to-clip converter, Arduino microcontroller, BLE4 module, soft potentiometer, wearable key, including textile push button, conductive thread, and enough. Pressure valve. A graphic representation of sensor jacket is given in this figure. A system of telemedicine is being developed by us. It employs the following approach: advanced sensing, signal processing, and public telecommunication are used for clinical monitoring of the patients located in their own community and for transmitting only the patient information online to a medical professional at a hospital at distance. The medical professional interacts with the patient remotely through audio and video links and simultaneously examines the data transmitted by the monitoring system and does medical assessment, diagnosis, and prescription. The medical professional may consult with other professionals online and may also use other available resources in arriving at the diagnosis and prescription. The use of human medical professionals to perform health assessment diagnosis, and prescription is far more desirable than the popular approach to telemedicine and telehealth, where an automated system may provide medical advice based on the input generated by the patient, which is known by the bias and prone to error. A schematic diagram of the proposed system is shown in this figure. The relevant issues of development and instrumentation for the system are listed as follows. Integrated mechatronic design of the sensor jacket to be worn by the subject for online health and monitoring. Selection of the embedded sensor and hardware, particularly with respect to their type, size, and features for acquiring the vital information from the subject, sensor location and configuration in the jacket to improve or optimize the process of data acquisition, power requirements and flexibility, signal processing and communication hardware on the sensor jacket, software for signal processing, artifact removal, data reduction, interpretation, and representation within the host computer and the patient app for transmission to the doctor's computer. Graphical user interface, GUI, at both ends, patient location and doctor location. Assistive methodologies for fast and accurate communication of information from the host computer at the patient and to the doctor. In the design of the sensor jacket, a mechatronic approach that employs to MDU, MDY, as a performance function is utilized. The design indices in the MDQ include such aspects as component location, accuracy, speed, size, complexity, maintainability, design life, reliability, robustness, fault tolerance, reconfigurability, flexibility, cost, user-friendliness, and performance expectations. Parameters such as sensor location and configuration in the jacket are decided so as to improve the process of data acquisition, body conformability, weight, robustness, cost, and so on. One of the ways that can reduce the spending of healthcare of the aging population is to explore the recent technological advancements in sensor systems, robotics, and information and communication technologies for providing high-quality supportive environment to people in their own home. A robotic home care environment may have autonomous robots which can be augmented with haptic teleoperation capability, comprising a haptic-assisted remote control robot to monitor and assist individuals within the home environment, as you can see in this slide. Specifically, the system will have the capability for two modes of operation. First, more autonomous operations for 24-hour routine-based care, mobility, bathing, dressing, toileting, meal preparation, providing medicine, monitoring, and seeking external help. And B, remote monitoring and haptic teleoperation in emergency situations, like until regular help arrives, ambulance, paramedics, police, firefighters, and etc. Haptic teleoperation will incorporate advanced sensing and actuating the capabilities of a robot, together with dexterity and cognitive skills of a human. Specifically, haptics incorporate the capability of feeling the condition and other forces of interaction at the remote side by the human operator of the master manipulator, in addition to the sensor in the robot, including the master and slave units for teleoperation. Additional sensor systems are necessary for monitoring the environment, which is dynamic, ultra-structured, and not fully known. Patient sensors for this application include optical encoder for motion sensing and torque sensor for the joints of the robot, and the master manipulator, tactile sensor for the robotic finger, laser and ultrasonic rain filter for the mobile platform. optical encoders for the fields of the mobile platform, cameras for the mobile platform and the work environment, and basic sensors for monitoring human health, like telemedicine. Common sources of water include surface water from catchment, lakes, reservoirs, rivers, waterways, etc. Groundwater from wells, springs, ocean water requires desalination, and rainwater requires collection and retention. Water is essential for human survival, for consumption, hygiene, irrigation, power, and sale. In developing nations, approximately 80% of diseases are water related. Treated wastewater is used for many uh, of Americans, Canadians, German, and Sweden countries. Groundwater is used by many for domestic use, like 26% of Canadians. And about 70% of water usage is for agriculture. Water contains naturally occurring substances like uh, bicarbonates, uh, sulfide, sodium, fluoride, calcium, magnesium, and potassium, and harmful contaminants like microbes and dissolved chemicals. Monitoring of the quality of water sources will not only benefit public health, but also the ecosystem. In particular, water quality can determine the ecological balance among species. The types of water quality parameters can be characterized in physical, like color, density, sediment, chemical, like dissolved inorganic material, and biological, like dissolved organic material or bacteria. Commonly monitored water quality parameters are pH value, temperature, conductivity, oxidation reduction potential, and dissolved oxygen. The manual approach is widely used to monitor the water quality by sensing the parameter. The process involves collection of water samples in the field and then testing them in laboratory. There are challenges this particle, including unavailability of proper sensors, cost of data loggers, and so on. In particular, the manual approach is time consuming and labor intensive, not convenient in relation with taking heavy and complex equipment to the field, may create safety problems for field workers, and is typically a low resolution monitoring process. Possible transportation of field test samples, the laboratory may distort their properties. This will cause inaccurate and non-representative test results. Also, this approach generally leads to delay in analysis and taking action, like generating advice. In view of these issues, an automated approach to spatio-temporal, like both geographic distribution and time variation, monitoring of water quality is desired. And the automated approach, the quality of water coming from various sources is automatically measured using several SN that are distributed over a large geographic area. The data acquired from the SN may be locally conditioned and then transmitted to a mother node, then to a base station, and finally to a central assessment unit using ICT. Spatio-temporal of the quality of water may be monitored and assessed, and appropriate actions can be taken in this manner. The general framework of the system is shown in this figure. In this platform, the SN may contain multiple sensors, for example, those for temperature, pH value, turbidity, dissolved oxygen, electrical conductivity, or oxidation reduction potential. These sensors are commercially available and may be used directly or with some modifications. A microcontroller system is used for sensor data acquisition at each SN. Most nodes are stationary, while some dynamic geographically movable modes may be implemented. The dynamic node may be in the form of propelled node inverter or node mounted on mobile robot devices that can navigate on ground. Low-level processing of sensory data is carried out by the microcontroller before transmitting the data through a radio transceiving to a more powerful node. Processed data from the SN are transmitted to a base station. There, the received data are subjected to high-level processing and data compressing, and are subsequently transmitted to a central computer called CAU. The CAU is a knowledge-based decision-making unit which accesses the data from different geographic locations in a temporal manner. Based on the assessment, the CAU provides advisory, alarm, REM, and other useful information of water quality at various locations, and also provides the rationale and explanations of these decisions. Policy decisions can be made based on the outcome. Furthermore, the CAU can optimize the operation of the ICT platform in order to make the system outcomes more accurate, uniform, and effective. It can map out regions having water quality problems at different levels based on a water quality index. An engineering system typically consists of a wide variety of components that are interconnected to perform the intended function. And now we will start new lectures for this part of new topic of lecture for this part. It's called component interconnection. When two components are interconnected, signals and power will flow between them. And as the two components interact, their signals or responses will vary with time, depending on the dynamics of both components. When two devices are interfaced, it is essential to guarantee that the resulting changes to the dynamic conditions of the system will not lead to an unacceptable performance. It is clear that considerations of component interconnection and interface between the connected components are important in instrumentation of an engineering system. Engineering systems are typically multi-domain systems, which consist of more than one type of components that are interconnected. This is particularly true with mechatronic systems, which employ an integrated and concurrent optimal approach in their design and development. Commonly, mechanical, electrical, electronic, and computer hardware are integrated to form practical applications. When components are interconnected, the behavior of the individual components in the integrated system can derive significantly from that when each component operates independently. It follows that component interconnection is an important consideration in the design and instrumentation and overall development of an engineering system. The nature and type of the signals that are present as the interface of the interconnecting components depend on the nature and type of the component. For example, when a motor is coupled with load through a gear or transmission unit, mechanical power flows at the interfaces of these components. In that case, the power that is transmitted is of the same type, and we are particularly interested in associated signals of the angular velocity and torque. Similarly, when a motor is connected to its electronic drive system, there is conversion of electrical power of the drive circuit into mechanical power of the rotor. Are you agree? Now, the interface may be represented by an electromechanical transformer, as shown in this figure. On one side, we have voltage and current and the power signals And on the other side, we have angular velocity and torque as the power signal. But we should note, in both examples, there will be energy dissipation of both sides, and hence the energy conversion will not take place at 100% efficiency. Generally, when two components are interconnected, dynamic interactions or dynamic coupling take place between them, and hence the conditions of either component will be different from what they were before the connection. It is clear that the interconnected components should be properly matched in order for the resulting system to operate in the desired manner. For example, in the case of a motor and its electronic derived system, maximum efficiency may be a primary objective. Then, the dynamic interaction between the two components will be significant. In contrast, in the case of a sensor and a monitor object, it is important that the dynamic conditions of the object would not be altered by the sensor, like the loading of the object by the sensor should be negligible. And in other words, dynamic interaction between the sensor and the monitor object should be negligible while maintaining the ability to accurately measure the required quantity. Component interface plays an important role in the proper operation of the interconnected system. Specifically, the interface has to be designed, developed, or selected depending on specific functions of the interconnected system. Matching of components in multi-component systems should be done carefully to improve the system performance and accuracy. In this context, impedance considerations are important because impedance matching is necessary to realize the best performance from the interconnected system, depending on its functional objective. The following considerations are relevant in component interconnection. First, characteristics of the interconnected component, like domain of the component, type of the component, like actuator, sensor, drive circuit, controller, mounting, or hub. Second, purpose of the interconnected system and communicated information, drive, measure, and so on. And third, signal and of power level of operation. And this part of the lecture addresses interconnection of components such as sensor, data acquisition, hardware, signal conditioning circuitry, actuators, power transmission devices, and mounting mechanics in an engineering system. The basic concepts of impedance and components matching are studied. Desirable impedance characteristics for interconnected components, depending on the purpose and application, are discussed. Several methods of impedance matching are presented, and their applications are indicated. Impedance matching in both electrical and mechanical devices is addressed. Discussion and developments given here may be rather general in some situations. However, the concepts presented here are applicable to many types of components in an engineering system. Impedance can be integrated in the traditional electrical sense as generalized resistance. It may be interpreted in the mechanical sense as well, or in a general sense with regard to other domains like fluid or thermal, as well, depending on the type of signals involved. For example, a voltmeter can modify the current and voltage in a circuit, and this concerns electrical resistance of DC circuit, or more generally, electrical impedance, when AC circuits are considered. As another example, a heavy accelerometer will introduce an additional dynamic load, which will modify the actual acceleration at the monitor location. This concerns mechanical impedance. As a third example, a thermocouple junction can modify the temperature that is measured as a result of the heat transfer into the junction. This conserves thermal impedance. Similarly, we can define impedance for fluid systems, magnetic systems, and so on. In general, impedance is defined as you can see at this simple expression. The across variable is measured across the two ends of the component, and the through variable transmits alternated through the component. So, as you can see here on the slide, impedance proportional across variable and inverse proportional through variable. Examples of across variables are voltage, velocity, temperature, and pressure. Examples of through variables are current, force, heat transfer, rate, and fluid flow rate. Even though electrical impedance is defined as voltage or current, which is consistent with this definition, mechanical impedance historically has been defined as force or velocity, which is the inverse of this definition. It is the mobility that is defined as velocity, and mobility should be interpreted as impedance in the general sense, like generalized impedance in other analysis. In instrumentation procedure, component interconnection is done in order to achieve some specific purposes. These impedances of the conserved components should be matched in order to improve the system performance with regard to these functional purposes. We will consider the following categories of objectives of impedance matching now. That's only four. First, maximum power transfer from a source to a load. 2. Power transfer at maximum efficiency. 3. Reflection prevention in signal transmission. And 4. Loading reduction. The efficiency of power absorption by the load is given by the fraction of the absorbed power from the total power, as you may see here from equation for eta. And we can see at this on the bottom expression here. Eta proportional to 1 over 2 times I squared times R1. R1 is here on this one. 1 over 2 I squared times in brackets R from line and RF. Or simply we can this simple expression on the right side. So in theory, we get 100% efficiency when the load impedance is infinite. Clear. The condition for maximum efficiency is quite different from the condition for maximum power. In fact, we see that the maximum power, the efficiency is only 50%. And this is indeed a condition of a rather poor efficiency. When an electric signal encounters an abrupt change in impedance, part of the signal will be reflected back. The reflection coefficient, G, we can see on the right side, and we can see here, G proportional V sub R over V sub I. So the reflection coefficient G is given by ratio of reflected signal V sub R to the incident signal where voltage V sub I. If a signal transmitted through the impedance Z sub C abruptly encounters a terminated impedance Z sub L, it's near its low, the corresponding reflection coefficient is presented here. A reflecting signal results in signal deterioration, both magnitude and phase angle, and dissipation, both of which are undesirable. It follows that, ideally, we like to have as G equals 0. Consider a source of internal impedance Z sub S, like 50 ohms, as shown in this figure. To avoid signal reflection at either termination point, no matter load, source, we must have the impedance matched conditions as you can see, is S dot equation. Z sub S is the same as Z sub C as a Z sub S. If the impedance matching is not presenting, it can be achieved with a grounding impedance or an impedance matching path. An example is shown in this figure. In this example, suppose that Z sub S not equal Z sub C, then the grounding impedance Z sub G has to be placed such that the following condition is satisfied is first equation here. I show you here. As you can see, it will be, I remembered this in previous slide. Here, 1 over Z sub S plus 1 over Z sub G, or equals 1 over Z sub C. Then, this arrangement provides an equivalent terminating impedance of Z sub C. Z sub C here at the source end. In a short cable, the reflected signal travels to its terminal very quickly and decays fast. Hence, signal reflection is not important in short cables. The principle of signal reflection may be used in practical applications. For example, since damage in a cable will result in an abrupt change in the impedance, there will be signal reflection at the damaged location. Then, by determining the time it takes for a voltage pulse to be reflected back to the source, the distance to the damaged location can be determined. This is the principle behind a reflectometer, which is used to detect damages in cables. Signal reflection is not limited to metal cables, like copper, aluminum, or another. For example, it can be observed in optical fibers and in acoustic signals that encounter a change in the acoustic impedance in the transmission medium. An adverse, sorry, where is my slide? 1 second, please. An adverse effect of improved impedance conditions is the loading effect, which distorts signal. The resulting error can be exceeded other types of error, such as measurement error, sensor error, noise, and input disturbance. Loading can occur in any physical domain, such as electrical and mechanical. Electrical loading errors may result from connecting an output unit such as, 1 second please, such as a measuring device or signal acquisition hardware that has low input impedance to an input device, such as a signal source or a sensor, with low to moderate impedance. Mechanical loading errors can result in an input device, like an actuator, because of inertia, friction, and other resistive forces generated by an output component connected to it. In engineering systems, loading errors can appear as phase distortion as well. Digital hardware also can produce loading errors. For example, analog to digital conversion hardware in a DAQ board can load to the amplifier output from a strain gauge bridge circuit, thereby affecting the digitized data. To obtain a model for loading distortion and a method for reducing loading effects, we now consider cascade connections of two-port electrical devices. A model for a two-port electrical device is shown in this figure A on the upper part of this slide. It shows, in particular, the input impedance Z sub I, as you can see in this part of the left, and the output impedance Z node of the device. They are defined in the following text. Input impedance Z sub I is defined as the ratio of the rated input voltage to the corresponding current through the input terminal, while the output terminals are maintained in open circuit. Output impedance Z sub O is defined as the ratio of the open circuit in case we have no load voltage at the output port to the short circuit current at the output port. Open circuit voltage that output is the output voltage present where there is no current flowing at the output port. This is the case if the output port is not connected to a load. As soon as a load is connected at the output of the device, a current will flow through it, and the output voltage will drop to a value less than at the open circuit voltage. To measure the open circuit voltage, the rated input voltage is applied at the input port and maintained constant, and the output voltage is measured using a voltmeter that has a high impedance. To measure the short circuit current, a very low impedance ammeter is connected to the output port. These definitions are given with a reference to an electrical device. However, a generalization to mechanical device is possible by interpreting voltage and velocity as a cross variable, and current and force as through variables as noted earlier. Then, mechanical mobility should be used in place of electrical impedance in the associated analysis. Similar generalization is possible for other physical domains as well. It is seen that the input impedance Z sub I and the output impedance Z sub O, as represented in this figure, I agree with their definitions given earlier. But we should notice that V sub naught is the open circuit output voltage. When a load is connected to the output port, the voltage across the load will be different from V sub naught. Are you agree? Look at this figure. Yeah, are you? Okay. This is caused by the presence of a current through Z sub naught. In the frequency domain, V sub I and V sub naught are represented by their respective Fourier spectra, or in the complex form with a real part and imaginary part for a magnitude and the phase. The corresponding transfer relation can be expressed in terms of the complex frequency response, the function like G from J omega. Under the open circuit, when we have no load conditions in these first equation, where V naught proportional G times Vi. Next, consider the two devices connected in cascade and shown in figure B in this here, in cascade device. It can be easily verified that the following relation form, as you may see in next equation for here, V naught 1 proportional G1 times Vi. This relation can be combined to give the overall input-output relation, as we can see in this equation, V naught proportional Zi2 over sum on the bottom part, Z naught 1 plus Zi2, and all of them multiplied by G2 and G2, G2 times G1 times Vi. Its ideally expected product G2 times G1 by the factor as you may see in the next equation bottom. We should be noted from this equation that cascading has distorted the frequency response characteristics of the two devices. And this represents the loading error. The loading error becomes insignificant than the Z01 over the Z01 I2 many times less than 1. So that we have 1 over 1, right? Because this very small value. And from this observation, it can be concluded that when two components are interconnected in cascaded form, in order to reduce the loading error, the input impedance of the second device, or we can say as an output device, should be much larger than the output impedance in the first device. A Lec network used as the compensation element of a control system is shown in this figure, in this example on the left side in figure A. Show that the transfer function is given by V naught over V sub I and proportional Z2 over R1 plus Z2. Z2 is proportional R2 plus 1 over CS. What are the input and output impedances of this circuit? Moreover, if two such large circuits are cascaded as follows in the B figure, that is the overall transfer function. How would you bring this transfer function close to the ideal result as meaning here Z2 over the sum of R1 plus Z2 in power 2? Let's start our solution. To solve this problem, just note that in a figure A, as we can see more detail here on the left, the voltage drops across the element R2, yes, and plus 1 over CS, right, is expression for our V naught here. And hence we can see V naught over the R. Now, the input impedance Z sub E is derived by using the input current as the next one, Vi over R1 plus Z2. And thus we can find a Z sub I. The output impedance Z naught, and the next equation here, is derived by using the short circuit current. Short circuit current is ISC, is simply Vi over R. So Z naught is here. Next, consider the equivalent circuit that show in figure C, as you can see here on this part. Since Z is formed by connecting Z sub 2, and in brackets we have R1 plus Z sub 2 is parallel, we have this equation as we can see on this part. 1 over Z, proportional 1 over Z2 plus 1 over the sum R2 plus Z2. In parallel, yes, and the voltage drop across Z is where the V naught prime, as you can see in the next expression, where the Z over R1 plus Z in times the Vi. Now, apply the single circuit model result I to the second circuit stage in figure B. We get, in this case, as the V naught proportional Z2 over R sum R1 plus Z2 and times V naught prime. Substituting this equation, we have V naught as simply Z2 over sum of R1 plus Z2. The overall transfer function for the cascade circuit can be seen on this right part of our expression. Z proportions V naught over Vi. After the transformation, we can get this expression. Now, substitution equation Iy for the 1 over Z, we get this big expression here. And we observe that the ideal transfer function is approached by making R1 times Z1, Z2, and over R1 times Z2 over the sum R1 plus Z2 squared. It's a small compared with unit. In case if you're studying impedance matching in mechanical systems, the concepts of impedance matching can be extended to mechanical systems and to mixed systems like electromechanical systems or mechatronics in a straightforward manner. The procedure follows from the familiar electromechanical analogy. Two specific applications are in a shock and vibration isolation and transmission systems or gears. These two applications are discussed as follows. So, a good example of component interconnection in mechanical systems is vibration isolation. Proper operation of engineering systems such as delicate instruments, computer hardware, machine tools, and vehicles is hampered due to the shock and vibration. The purpose of vibration isolation is to isolate such devices from undesirable vibrations and shock disturbances that come from its environment, including the supporting structure or rod. This is achieved by connecting a vibration isolator, or shock mount in between them. External disturbances can reach a system in the form of force or motion input. And depending on that, force isolation related to the force transmissibility or motion isolation related to motion transmissibility and would be applicable in design of the isolator. Luckily, the isolator design is quite similar for the two situations. In force isolation, vibration forces that would be ordinarily transmitted directly from a source to a supporting structure are filtered out by the isolated through its flexibility or spring and dissipation or damping, so that part of the force is routed through in inertial path. In motion isolation, vibration motions that are applied to a system like vehicles by a moving platform are absorbed by an isolator through its flexibility and dissipation, so that the motion that is transmitted to the system or interest is weakened. The design problem in both cases is to select applicable parameters for the isolator, so that the vibration entering the system of the interest are below the specified value within a frequency band of interest. This design problem is essentially a situation of mechanical impedance matching, because impedance parameters of the isolator are chosen depending on the impedance parameter of the isolator. But note, as indicated before, generalized impedance across variables corresponds to the mechanical mobility, which is the inverse of what is traditionally called mechanical impedance. Force insulation and motion insulation are represented in this figure. In figure A, vibration force at the source is F from T, as you can see here on the top. In view of the isolator, the source with mechanical impedance Z sub M is made to move at the same speed as the isolator with mechanical impedance Z sub S. This is a parallel connection of impedance. Hence, the force F from T is split so that part of it is taken up by the inertial part of broken line of Z sub M, and only the remainder Fs is transmitted through Z sub F to the supporting structure, which is the isolated system. Force transmissibility, as you may see at the first equation from the T from F. T sub F proportional F sub S over F, or Z sub S, and we have here on the top, bottom, Zm plus Zf. In figure B, vibration motion V from T of the source is applied through an isolator with impedance Z sub S and mobility M sub S to isolated system, and analogical mechanical system M sub F. The resulting force is assumed to transmit directly from the isolator to the isolated system, and hence these two units are connected in series. Consequently, we have the motion transmissibility, as you may see here in the next equation. T sub M proportional V sub M over V. Over some transformation, we can get Z sub S, and over Z sub S plus Z sub M. And as a result, usually both types of isolator can be designed in the same manner using a common transmissibility function T. Simple example of force isolation and motion isolation are shown in these figures C and D. First, we obtain the transmissibility or force transmissibility function for system in figure C. Then, in view of equation, the motion transmissibility of the system in figure D is equal to the same expression. First, consider the force transmissibility problem of figure C, which is shown again in figure E. This may represent a simplified model of a machine tool and its supporting structure. Clearly, the elements M, V, and F are in parallel, since they have a common velocity V across them, and hence its mechanical impedance circuit is shown in figure F on the bottom part of the slide. In this circuit, the impedances of the basic elements are Zm proportional Mj omega, Zb equal B, and Z chi K equal K over J omega. For mass, spring, and viscous tamper B, and respectively. All details we may see in this table. Substitute the element impedances into the force transmissibility expression, which is obtained by using the laws of element interconnection shown in this figure, and the circuit as in previous figure, figure F. I see we have not enough time now, so we can continue this topic on the next lecture. I hope, as usually, you enjoyed this lecture, and I'm looking forward to see you next time. Bye.